All right, so now we're in section 3.2, and we're going to look at some more complex probability theory. The first thing we need to look at is the idea of conditional probability. Conditional probability is the probability that an event occurs given that another event has already occurred. It's denoted the probability of B given that A has occurred. All right, so let's find a conditional probability. Suppose we're going to select two cards from a standard deck of 52 cards. And we want to know what's the probability that the second card is a queen given that the first card is a king. Assume that the king is not replaced. Well, there's 52 cards in a deck. And we know that one has been taken out and is on the table, and that card is a king. So there's 51 cards left in our deck, but all 4 queens are there. So the probability of the second card is a queen, given that the first is a king, is 4 out of 51, or 0.078. Here's another example of conditional probability. Suppose we're going to look at IQ in children and whether they have a particular gene present or not present. And we looked at 102 children. Let's find the probability that the child has a high IQ, given that the child has the gene. Well, we're not considering all 102 children any longer. We are considering only these 72 children in which the gene is present. And of those 72, 33 have a high IQ. So we see that the probability of having a high IQ, given that the gene is present, is 33 out of 72, or 0.458. Here's another definition that we're going to need, the idea of independent or dependent events. Two events are considered to be independent if the occurrence or non-occurrence of the first event does not affect what happens to the probability of the occurrence of the other event. For example, if my two events consist of tossing a coin and getting heads, and the second event is roll a die and have it land on 2, whether I get the head or don't get the head on the coin toss has no effect on what's going to happen to that die roll. So those are independent events. Events that are independent means that the probability of B, given that A has occurred, well, A has not affected B at all, so this is just equivalent to the probability of B, and also vice versa. If events are not independent, we say they are dependent events. Let's decide whether this event is independent or dependent. We're going to select a king, not replace it, and then select a queen. Well, the fact that we did not replace it means we have changed the probability of getting a queen. If the probability of getting a queen by itself is 4 out of 52. But if we selected 2 cards and we selected a king and didn't put it back, then the probability of the second card being a queen, given that the first was a king, is 4 out of 51, but the probability of getting a queen is 4 out of 52. Those two values are not equal, thus those events are known as dependent events. The probability of that first draw did change the probability of the second selection. Now we have a coin and a die, and we just saw a minute ago that those are independent events because no matter whether we get the head or don't get the head, it is not going to change the probability of getting the 6 on the die. So those two events are independent events. The multiplication rule is used to find the probability of two events A and B occurring in sequence. The probability of A and B is equal to the probability of A times the probability of B, given that A has occurred. But if the two events are independent, then the probability of B, given that A has occurred, is just equal to the probability of B. So the probability of A and B for independent events is just the multiplication of the probability of A times the probability of B. And this can be extended to any number of independent events. So let's find some probability using the multiplication rule. 2 cards are selected without replacing the first card. Find the probability of selecting a king and then selecting a queen. Well, the probability of getting the king is 4 out of 52. Then the probability of a queen, given that the king was drawn and not replaced, is 4 out of 51. 4 times 4 is 16, and 52 times 51 is 2,652, which is approximately 0.006. While the probability of the coin toss and the die roll is the probability of getting the head is 1/2, the probability of rolling the 6 is 1/6, so the probability of a head and a 6 is 1/2 times 1/6, or 1/12. Suppose, let's look at one more example, the probability that a particular knee surgery is successful is 0.85. Now it's important to notice here that surgeries are independent of each other. If the surgery one is successful or not successful does not affect what the second patient. So let's find the probability that 3 knee surgeries are successful. That means the probability that the first one is successful, and the second one is successful, and the third one is successful. When we say the word and, we think multiplication. So 0.85 times 0.85 times 0.85 is approximately 0.614. How about finding the probability that none of the knee surgeries are successful? Well, the complement rule tells us if 85% are successful, then 15% are failures. And so the probability that none of the surgeries is successful means the first one's not successful, and the second one is not successful, and the third one is not successful. 0.15 times 0.15 times 0.15 is 0.003. Now find the probability that at least one of the knee surgeries is successful. Is a little more complex than it really looks when you first read this very simple sentence. It is easier to realize that at least one means 1 or 2 or 3 of them were successful. The complement of that is that it's 1 minus the probability that none are successful. We saw in the example before that the probability that none were successful was 0.003. 1 minus 0.003 is 0.997. All right, we're going to skip this example, and we are now at the end of section 3.2. It's time for you to go to the Course Compass My Math Lab and do homework 3.2.